guys, so prior to this, we were talking about using annihilators to solve these non-homogeneous linear differential equations. The annihilator method is really great, and we have the table of annihilators, and we just go through that three-step process that I showed you before. But turns out sometimes the annihilator method isn't going to work for us. And I'm going to show you a quick example of that. This equation that is in this box here is a second-order differential equation. But if you look at the right-hand side of the differential equation, you'll recognize this function, capital F, is not in your table of annihilators. Okay? And when you think about taking derivatives of fractions, as you take derivatives of fractions, you have to use the quotient rule. And in so doing, you end up with some very complicated derivatives, right? So as you take derivatives of this, things don't get simpler, they get more complex. And in fact, it turns out that there is no annihilator for this. There is no annihilator. So if there is no annihilator for the function that is on the right-hand side of your differential equation, then you're not going to be able to use that method, of course. Annihilators are great for powers of x, sine and cosine, and exponential functions, and combinations of those. But when you have fractions like this, this is not the sort of function that is going to be well suited to the annihilator method. So what I want to talk to you about for a few minutes right now is an alternative method that we can sometimes get away with to help us solve these differential equations. It's called variation of parameters. Okay? And variation of parameters is also a very nice method. I'm going to just show you an example here, basically this example. And I'm not going to explain in this video why the formulas that I give you really work. I'm going to save that for class. But I at least want you to see an example of how this works. Basically, there are still the same three steps. The same three steps that we learned about for the annihilator method are still used for the variation of parameters method as well. So the first step, of course, is to find the complementary function. So I need the auxiliary equation in order to do that. Here's the auxiliary equation, r squared minus 12r plus 36 equals 0. This one factors very nicely. R minus 6 quantity squared equals 0. Okay, and so r is equal to 6 and 6. We have a repeated root this time. Okay, so we can write down our complementary function already. The complementary function would just be c1 times e to the 6x, and because it's a repeated root, the second term, which has c2 in front of it, would be x e to the 6x. So this is the complementary function. Okay? Now I want to just identify really quickly these two basic solutions, which I'm going to call y1 and y2. Those are the two individual solutions that we are building this linear combination out of. The y1 and the y2 are going to get mentioned in the variation of parameters formula, so I thought it would be good to have those labeled before I go any further into it. So this part so far is nothing new. We're just doing step one of the process for solving these differential equations. Now step two is where we're going to start doing something new, which is the variation of parameters method. Basically, first of all, I also should mention, we're only going to do variation of parameters for second order differential equations. So if you see a differential equation that's higher than second order, we're not going to use this approach. You can actually use variation of parameters for higher order equations, but it is really, really tedious to do by hand. You would be much better off using a computer to do it. So for the purposes of doing things by hand that just give you the idea of the method, second order differential equations are what we're going to want to use. I should also mention that I'm going to be expecting you to determine which method to use, the annihilator method or the variation of parameters method. So you have to look at this right-hand side function here, this capital F, and you have to make that determination. Do I know how to annihilate this or not? If you do, great, you can use the annihilator method. But as is the case here, I don't know how to annihilate this function, so I'm going to use the variation of parameters method. So step 2, this is where the new stuff comes in. What we are basically going to do is we are going to guess what the particular solution is going to look like. And the way that the guess is going to look is we're going to vary the parameters C1 and C2. So we're going to write down a guess. Instead of C1, I'm going to allow it to vary as a function of x. So U1 times Y1 plus U2 times Y2. So it has the same structure as the complementary function does, but instead of constants in front of Y1 and Y2, we are going to have variables. Okay, so we are varying the parameters. That's kind of where the name comes from. Okay, and in this formula, the U1 and the U2 are to be determined. Okay. Now, basically, I'm going to derive in class formulas for U1 and U2, but for this video, I'm just going to give you those formulas. Okay, we're just going to use them to practice on this example. So here are the formulas that you're going to need. Okay, turns out, very nice, and it's a nice derivation because it uses some linear algebra as well. So I'm going to save that for class. But let me just give you the formula here. U1 is going to be negative the integral. So yes, you're going to have to do some integration. Negative the integral of y2, this is the y2, the second function that was in our original complementary solution, times f, which is the function on the right-hand side of the differential equation, all divided by the Wronskian of y1 and y2. So the Wronskian is going to make a reappearance in this section as well. Okay, so that's the formula for U1. And then the formula for U2 is similar, but not quite the same. First of all, there's no minus sign on the U2 function. And we're going to integrate y1 times f and divide by the Wronskian. So the way I usually remember this is just that the subscripts are opposite, right? The U1 goes with the y2, and the U2 goes with the y1. All right, and we multiply by the function f in both cases on top, and the Wronskian ends up on the bottom in both cases. All right? So for this particular example, what we can do is work out the U1 and the U2 and then write down our particular solution. Now I'm going to erase this complementary function, but you're going to want to keep it handy because remember that step 3 is where you have to take the complementary function and add it to what we're coming up with here in the particular solution. Okay, so let's work this out. Now, I like to do my Wronskian first so I don't have to wonder what it is in the middle of the calculation. So here are the y1 and the y2 that we had already found. What I'm going to do now is just find the Wronskian of y1 and y2. So just do that kind of up front. So it's the determinant. Remember how we do this. We put our functions on the first row, so e to the 6x and x e to the 6x. That goes on the first row. And then on the second row, we simply take derivatives of the row above. So 6e to the 6x. And on the second term, I actually have to use the product rule. It's going to be e to the 6x plus 6x e to the 6x. Okay? So there's my 2 by 2 matrix that I have to now take the determinant of. All right, so I'm going to use the AD minus BC formula here. I'll have e to the 6x times e to the 6x plus 6x e to the 6x. And then minus, the opposite diagonal has a 6x e to the 6x and e to the 6x again on it. Right? Of course, e to the 6x times e to the 6x is just e to the 12x. So I'm just going to multiply this out really fast. We're going to end up actually discovering here that almost everything cancels. Only thing that we have to keep track of is the e to the 12x part. Okay? So my Wronskian is e to the 12x. Great. Okay, so then I now can come back and start working out what U1 and U2 are using these formulas right here. So let me just do that for this example. Okay, again, all I'm doing in this video is an example. I'm not showing you the theory behind it, which I'm going to do later. All right, so for the example, u1 is just negative of the integral of y2. So just remember, I've erased it now, but y2 was x e to the 6x, right? Times the function capital F, that's just the right-hand side of the original equation, e to the 6x over 1 plus x squared. And then the Wronskian has to go on the bottom, that's e to the 12x. So this is the integral that we need to do. I'm going to erase my Wronskian now. I don't need that right now. Okay. E to the 12x was the Wronskian. This is the integral that I have to do to find u1. Right. Okay, notice actually all of these exponentials cancel off. E to the 12x on top and on the bottom. So I'm only left with integrating the negative of x over 1 plus x squared. This integral can just be done by a substitution. If I put a 2 here and a 1/2 out in front, I have negative 1/2 of the integral of du over u. Well, the antiderivative of du over u is the natural log of u. So we get the natural log of 1 plus x squared. Normally, we would put a plus c on the end of integrations like this, but we are only looking for one particular solution, remember. So it's okay to just take c to be 0. I don't have to actually write it down here. Okay, so that's u1. And then the other formula is u2. u2 is positive the integral of y1, which was e to the 6x, times f, which is e to the 6x over 1 plus x squared. And then e to the 12x goes on the bottom again. So this is the integration that we have for the u2. Again, I'm just using this formula right here for u2. All right? Great. So as before, the exponentials all cancel out. I end up just getting 1 over 1 plus x squared. And that might have some bells going off for you because that's a pretty familiar integral. The antiderivative is just the arctangent or inverse tangent of x. Okay? So we have our u1 and our u2. Assuming you believe me that these are the right formulas for u1 and u2, we've found them. And so now I can write down my particular solution. So I'm going to do it right here. The particular solution is u1 times y1. So u1 was negative 1/2 ln of 1 plus x squared times y1, which was e to the 6x from earlier, okay, plus u2. u2 is the arctangent of x times y2, which was x e to the 6x. Okay? So this then is my particular solution. That's the particular solution. So this is the alternative way, the variation of parameters way of finding the particular solution when I don't know how to annihilate the function capital F on the right side. Okay? Step 1 and step 3 are totally the same as before. So what we can do now is we can simply come back and write down the final answer. Step 3 is where we just put it all together. We just have to write down the whole final answer. So y of x equals, there's the complementary function, which we had found earlier. I erased it, but I'll write it down again. It's c1 times e to the 6x, right? Plus c2 x e to the 6x. That's the complementary function. And now, on top of that, I need to add, which means I'm actually going to start with a minus here. I have to add this. Okay? So minus 1/2 ln of 1 plus x squared times e to the 6x. And then finally, plus the arctangent of x times x e to the 6x. So this is the final answer to the problem. Okay? So the outline of the steps is the same as the annihilator method. There's 3 steps, and the middle step is the one that's different. And there's just a formula for the particular solution that you have to learn. u1, y1 plus u2, y2. And the formulas for u1 and u2 are well known. So there's nothing mysterious about this, really. It's a very follow the procedure type of thing, and you're going to get the right answers to these. Hopefully this makes sense. I will come back and derive a little more why this works in class. I don't want to do that right now on a long video session at this point. I just wanted you to get the idea of the examples, and maybe you could try looking at some of these problems then before you have to actually focus on the homework. So this is variation of parameters for second order differential equations. Again, let me know if you have any questions. All right, thanks guys.